Hello everyone, and thanks for joining me. In this video we're going to start talking about normal distribution, and we want to start with two real-world examples. First one is from the world of manufacturing, and let's assume that you are manufacturing ball bearings. Well, in a perfect world, every ball bearing that you're producing, you would like to have a diameter of 25 millimeter, let's say, right? And everything is in control. You have a new equipment, you have trained technicians, everything seems pretty stable, and the process is stable, but there is some random noise in your manufacturing process. When you check the exact diameter of every ball bearing that you manufactured, you realize that it's not exactly 25 millimeter. It's pretty close, it's very close, but it's not exactly. There is some random variation in that. And those random variations could be due to, material properties, equipment performance, operator performance, or environmental conditions. Due to many of these factors, you would realize some random noise around 25 millimeter. One ball bearing is 25.002 millimeter. The other ball bearing is 24.995 millimeter. So it's not exactly 25 millimeter every single time. There is some random noise. And you see this behavior in other examples, like, for example, repair task completion. In a perfect world, every time a repair technician completes a certain repair task, it would require exactly 4 minutes. But that's in a perfect world. But we know that it's not going to take exactly 4 minutes. There is some random noise around that value due to many reasons. Equipment conditions, technician performance. There are different reasons that would cause that random noise. If we study these examples further, we would conclude that the ball bearing diameter is normally distributed with an average or mean of 25 millimeter and some standard deviation sigma. And that sigma here represents that random noise that exists. The 25 millimeter is the average. Same with the repair task completion. It would be normally distributed around 4 minutes with some standard deviation sigma, and that is again due to random noise. A lot of these examples in real world, you would realize that they follow a normal distribution with some average and some standard deviation, and that would clearly represent the random behavior of that random variable. Well, let's get into the detail of normal random variable. Normal random variable x, let's say, has two parameters, and those two parameters are mu and sigma, mean and standard deviation. Therefore, we notate that as x follows normal distribution with mu and sigma squared. So this is variance. The second term that it is specified when you specify a normal random variable is the variance. So if I tell you that a normal random variable x is normal with mu of, let's say, 4 and 9, this 9 here is variance, which is sigma squared. So if you're looking for sigma, that would be square root of 9, which is 3. So keep that in mind. That is very important and causes a lot of mistakes when you're calculating probabilities associated with normal random variables. The range of this random variable is unbounded. That means x can literally be any value. But the probability that your diameter of the ball bearing is 100 millimeter is very, very, very tiny. But according to normal distribution, there is a little chance for that. But obviously, there is a lot greater chance that the diameter of those ball bearings is 25 or around that 25 millimeter. The PDF, probability density function of normal random variables here is a little bit ugly, but we'll deal with that in a different way, and we'll talk about it. Let's take a look at the famous normal bell curve. And let's talk about that and what is it. And I want to take the same example of ball bearing. You know, X follows a normal distribution with 25 millimeter mean and some standard deviation. And let's assume for now that is only 1 millimeter. Okay. So you're manufacturing ball bearings and you studied the process and you figured that the diameter of these ball bearings has an average of 25 millimeter and variance of 1 millimeter. Well, this bell curve here represents a normal distribution. And this horizontal line here represents the range for X. Well, the range of values for X is really unbounded. So this line goes to positive infinity and negative infinity, but we know that the average diameter is 25 millimeters. So with a great probability, the average of these diameters is very close to 25. This bell curve here represents the probability of any diameter. And we know that with the highest value, the probability is going to be 25. So that's why the peak of this distribution is where the mean is. So this curve here represents the probability of any value on this graph. As you move away from 25 millimeter, you know, let's say 26 millimeter or 24 millimeter, there is a smaller chance for those values. And that is why the bell curve starts to go down as you move away from the average of that random variable. A very important characteristic of normal bell curve is that the area under this curve is equal to 1. That means the 100% of probability is represented by the area under this curve. But we know that this curve is really unbounded. As you can see, these two lines have not touched each other yet. So this goes to infinity, really, and this goes to negative infinity. So theoretically, that area is equal to 1. But because the range of normal random variables is unbounded, it's not going to be exactly 1. But we can approximate that after some point, let's say here and here, the area between these two lines, that shaded area, is approximately equal to 1. It's exactly probably 0.9999 something, but we can approximately say that it's equal to 100%. So the area under this curve really represents probability. If you were to calculate probability that the diameter of these ball bearings between 26 and 24, you would have to calculate the area under the curve here. That would be the probability of X between 24 and 26. Likewise, if you want to calculate the probability of the diameter between 27 and 23, you would have to calculate a larger area. And that area would be here. That's the probability of the diameter being between 27 and 23. So you can see as you move away from the average, probability of x being between two values increases. If you study normal distribution further, you would realize that for any value of mu and any value of sigma, there is a rule, and that is for any values of mu and sigma, probability that your random variables between mu plus sigma and mu minus sigma, so let's say that here is the mu, in our example was 25 millimeter, and mu plus sigma was 26 millimeter, mu minus sigma was 24 millimeter. But for any value of mu and sigma, the probability of x being between those values is 0.683. So that means this area, it's always 0.683. About 68% chance. As you move away one more standard deviation to mu plus 2 sigma and mu minus 2 sigma, well, that area becomes larger, and now it is equal to 0.955. 95.5%. And if you increase that a little further to 3 sigma, mu plus 3 sigma, mu minus 3 sigma, that probability is very close to 1. And that's essentially the limits that we consider as 100% of the probability. Because this value is very close to 1, the 3 sigma limit to the right and 3 sigma limit to the left, that area, we consider that as approximately 100%, but it's exactly 0.997. So in summary, for any value of mu and sigma, the probabilities will be like this. Before we look at one example here, I want to point out something, that if there is another manufacturing facility that was producing the same ball bearing, and they had a different normal distribution, let's say 25 millimeter average, 4 millimeter variance, how would the distribution of that look like? This means the mu is 25 and the sigma squared is 4, therefore sigma is equal to 2. So standard deviation in this case is 2 millimeter, not 1 millimeter that we had. So that means for this random variable y, for this new manufacturing facility, the distribution has the same average, right? But a larger standard deviation, a larger random noise associated with their manufacturing process. So if you were to sketch their normal distribution, it would be a distribution that is a lot wider, right? Something like this. Well, the area under that curve would still be equal to 1, 100% of probability, but the distribution is wider compared to the distribution of x, because they have a larger random noise. They have the same average though, but it's just more variable. So with that in mind, I want to take a look at this example. Sketch the probability density functions, essentially the normal bell curves, of the following random variables on a single plot. A is a random variable with normal distribution. Mu is 100, sigma squared is 10 squared, so sigma is 10. Similar parameters for B and C. Try to sketch these three normal bell curves on a single plot so that you can compare them.